Well friends, in the last lecture I told you that as far as this topic of the performance of feedback systems is concerned, we will be covering two more things. One, the discussion on steady state accuracy, and then a complete design example. I hope we will conclude our discussion today on this subject. Let me take up the aspect of steady state accuracy. I have taken it earlier, now I just give it a different quantitative color. The word steady state accuracy is not new to you. You know that by final value theorem you can determine the steady state error of a system. So let me give some quantitative information about it as to how to handle it when we enter into a design cycle. For that, for this quantitative description, I take this block diagram. GS is the plant model, and let me say DS is the controller in cascade, and I consider the steady state accuracy to standard reference input or command signal. Of course, if you have a disturbance signal, you can establish a block diagram between disturbance in the output and apply the basic steady state error relationship between the disturbance in the output. There is no problem. But the standard results I am going to give you between this input, the command input, are the output Y and the error E. It is your standard feedback system. You know that ES is equal to 1 over 1 plus DSGS into RS. You will note that now the GS in the relation we have used earlier is being replaced by DSGS because the total forward path transfer function or the total open loop transfer function of the unity feedback system is DSGS. I am splitting it into these two parts because studying the total system with respect to this configuration will turn out to be easier when I take a PD, PI or a PID control scheme. Okay? So this result is known to me very well, and I know that by application of the final value theorem I can get the value of the steady state error. So ESS equal to limit S tends to 0, it is ES. This becomes the steady state error. So let me substitute for ES. It is limit S tends to 0 SRS divided by 1 plus DSGS. Okay. Now please consider the situations one by one. We said that we will handle three situations only. One, a step input. So let me say a unit step input, because that really does not matter, because the steady state error will be scaled up or down depending upon the magnitude of input I am taking. For a unit step input, you know RS equal to 1 by S. Okay, and therefore your ESS becomes equal to limit S tends to 0. Look, it is 1 over 1 plus DSGS. With S gone, removed, with S cancelled, the limit is given by limit S tends to 0 1 over 1 plus DSGS. Okay. So let me put it again here. RS is equal to unit step 1 over S, and steady state error is equal to limit S tends to 0 1 over 1 plus DSGS, which can be written as 1 over 1 plus limit S tends to 0 DSGS. Why did I write in this particular form? The reason being that I will recognize this as equal to 1 over 1 plus Kp, where Kp in the literature is referred to as position error constant. Very important term in the literature because it is extensively used to describe the steady state error. So it means instead of specifying the steady state error of a system to a unit step input, equivalently you can specify that the Kp of the system is this much, where Kp is called the position error constant. The word position is coming because the step input signal in the so called motion control systems is the position input. You please see, I think at this point itself, let me explain this particular point. You have step, ramp and parabola. These are very general terms. These are the mathematical terms, you see, because the function is described mathematically by step, ramp or parabolic function. But in control system jargon, it is quite commonly used, this particular input as a position input, this particular input as velocity input, and this particular input as acceleration input. The reason is simply that in motion control systems, the step really corresponds to position, the ramp corresponds to velocity, and the parabola corresponds to acceleration. But the meaning of the words position, velocity and acceleration will change if your system is, let us say, a temperature control system or a liquid level control system. Still, you see, if you don't confuse yourself, then in that particular case the words position and step, velocity and ramp, acceleration and parabolic could be interchanged. You see, you keep in mind that these also are functions, and these functions mathematically are given by step, ramp and parabolic. So we will go ahead with the terms used in the literature. In the literature, Kp has been referred to as position error constant. But this you will definitely keep in mind that this position error constant really does not mean that it is applicable only to position control systems. It is a very general term, may be applicable to any system wherein the step input is being given, and for that system I can say now the steady state error is equal to 1 over 1 plus Kp, and this particular steady state error can now be given in terms of ESS or Kp only, where Kp, let me give you as a final formula to you, limit s tends to 0 ds/gs. Go to the next input. I go to the ramp input now. The ramp input is, as you know, Rs equal to 1 over s squared. Please help me. Give me the value of steady state error for the ramp input. ESS, as you can see from the formula you have, I am directly putting this result, limit s tends to 0, it is 1 over s ds/gs. Please check this whether this is okay. I have substituted Rs is equal to 1 over s squared in the standard result and let s go to 0. Okay, this is for you to verify. I remember the final result, that is why I have put it in this form. Okay, if that is okay with you, in that particular case I rearrange this result in the form ESS is equal to 1 over kV, where kV is equal to limit s tends to 0 s ds/gs. You see, this kV in the literature is referred to as velocity error constant. You see, I am giving you now equivalent ways of specifying the steady state accuracy. The only point is this, that if I give you system kV is equal to this much, it should automatically be clear that the input to the system is a ramp input. I need not specify that. While if I give you steady state error, I will have to specify the input along with. So this is an equivalent way. Kv is the velocity error constant. And lastly, and identically, of course, Rs is equal to 1 by s squared if you take. Please do it for yourself. ESS will turn out to be equal to 1 over Ka, acceleration error constant, where Ka is equal to limit s tends to 0 s squared ds/gs. This is your Ka expression, please. And that's all. You need not go to higher order inputs, because we have decided that we will go for ramp, step and parabolic inputs. And therefore, the conclusion of this discussion is this, that the steady state accuracy can be described either in terms of steady state error with a specified input, or equivalently I may give you Kp, Kv or Ka of the system. These are the error constants of the system. However, you will have to keep in mind that these error constants are defined for step signals, for unity signals, unit step, unit ramp or unit parabola. If your steady state, if your input is other than this, in that particular case, appropriate scaling you will have to do. This you have to keep in mind, and the scaling will become straightforward. Okay? This is the point I wanted to introduce. One more point I want to introduce is the following. I have the relationships for these three. Let me look at Gs as a general expression. Gs or ds/gs. Why Gs? the total forward path transfer function now is dsgs with respect to the block diagram I have taken. I hope you won't mind if I put it in this form, I s minus zi divided by s to the power of n j s minus pj, where zi and pj are poles and are zeros and poles respectively, and s is also a pole at s is equal to 0 of order n. Now you can just keep in think in your mind as to whatever type of transfer functions we have so far discussed can always be put in this particular form. It is a very general form. It is going to be convenient in the analysis I am going to make. That is why I have written in this form, but this is a very general form. All the transfer functions we have handled so far can definitely be put in this particular form, a constant, zeros, integral. The only thing is that specifically the poles which are at s is equal to 0 I have taken out, that is all, and my attention is going to be focused on this particular point. That is why the poles which are on the origin of the s plane have been specifically pointed out, otherwise all others are poles. These poles may be complex conjugate poles, these poles may be real poles, and whatever may be the general nature, there is no problem at all. Anyone who answers this question, can n be negative? Yes, it can be, there is no problem, but I have not taken the zeros on this specifically because that does not disturb me. Let it be 0. This, as you will see, has a specific role to play. That is why the poles at s is equal to 0 with n greater than 0 I am taking. He is very right, n can be negative, but I want to focus attention on the poles on the s plane. The negative n will mean that there is a 0 in on the origin at the s plane. Well, in that particular case I am capturing it by one of the zi is equal to 0. Okay, I am capturing it that way because it is not disturbing my analysis. Is it okay, please? I hope you got his point. So for me now n is positive. I think yes, let me in that particular case make it very clear that n is greater than equal to 0. It could be equal to 0 of course, as if there is, in that particular case there is no pole on the origin. Now you see that in all the formulas which we have seen for Kp, Kv and Ka, your limit goes, s goes to 0 in dsgs or s multiplied by dsgs or s squared multiplied by dsgs. Now if you look at this expression, if s goes to 0, please see that this is not going to create any problem, and same will be the situation he pointed out whether if n is negative, and s in the numerator also is not going to create any problem for me because the corresponding magnitude will be 0 and 0 is a defined number, does not create any problem for me. This is also, if I let s is equal to 0, this does not create any problem for me, but if I put s is equal to 0 here, this number becomes infinity, and therefore as far as the steady state accuracy is concerned, note this point please, this factor s to the power of n is going to play the primary role there. The major contributory factor to affect the steady state behavior of the system is the factor s to the power of n. Yes, please.
So for this we should actually take out all the s's from the numerator, because suppose we have s square in the denominator and s square in the numerator also, then this won't go to infinity. So s over n should be the net.
Right, I get your point. It does not mean that s to the power of n here will go to infinity for every input we are taking. You see, for at least this is there, that for some inputs, for example, depending upon the value of n. So if there is a cancellation, naturally it will not be there. But I am making a general statement, and after the general statement I am going to substitute specifically the values of Rs and see which power of n creates problem for us. His point may please be noted that for every value of n it is not going to create problem, because after all this is going to get multiplied with s squared depending upon the type of input we are going to handle. So I am making a general statement at this point that this s to the power of n may create problem, will create problem. Let us at this juncture not use this statement. So this may create problem, and that will depend upon the nature of the input, and if it does, in that particular case you feel that it is because of the infinite contribution it is giving to the magnitude of ds gs, at s is equal to 0, and specific cases in response to his question will automatically come when I take the different values of r s here. Okay. So, it is because of this only, you see, a specific name has been given to this system with respect to s to the power of n. Please see that if n is equal to 0, the system is referred to as a type 0 system, okay, because it is a major role to play, as you will see. His question also will get answered when I take the values of inputs. But this s to the power of n, this s to the power of n which corresponds to poles on the origin, or which corresponds to number of, see this statement please, number of integrators in the forward path of the system. Is it okay? This 1 over s to the power of n is n integrators, number of integrators. Why do I make this mention? Because you can suitably, with the help of your controller ds, control the number of integrations in the forward path. PI controller, for example, is an example by which you are introducing an integrator in the forward path by design. You are intentionally introducing integrators, and it will become clear by this analysis as to why the steady state error to step input will always be 0 when an integrator is introduced. This will become clear. We have always, all the examples we have taken so far, we have seen that the steady state error was 0 whenever there was an integrator. Okay, this will become clear, but at this point this may please be noted that number of poles at the origin is same as number of integrators in the forward path, and number of integrators you can control by suitable control on ds. And therefore, if you require a specific type of steady state behavior, maybe you can realize it by controlling number of integrators in the forward path. This question which I am posing to you will get answered automatically when I take the different values of n with the different values of input combinations. Okay? So, I made a mention n is equal to 0 is referred to as a type 0 system, n is equal to 1 obviously is a type 1 system, and n is equal to 2 is a type 2 system. Not that the type number stops here, it will be type n system in general, but we are stopping here with the observation that normally we do not come across systems which are more than type 2. Okay? So, this is known as type number of the system. Type number is primarily related to the steady state error behavior, the type number. Now, let us see how the type number is going to affect. Yes, please.
What would be the type number of a system, say s by s squared?
S by s squared is a type 1 system obviously.
But that means you're cancelling the pole and 0.
Surely.
But you said that in practical cases you can never.
You see that when you say s by s squared, it means you are giving me a model. So, it means this is 1 by s. Now, if you say the practical questions, it means practically this system with this particular transfer function will approximate an integrator, will not be exact integrator. After all, when you say s by s squared, it means this 0 is at least close to the pole at the origin. So, it means the real system, one thing is there 1 by s, you have a perfect integrator. So, this particular system with this type of behavior will approximate an integrator because of imperfect pole 0 cancellation. But it does not mean that there will not be equivalent effect. The only thing is that the perfection which is represented by this equation will not be realized in an actual system. This is what I made a statement. So, since type number is defined with respect to mathematical model, I will call this as a type 1 system. Okay?
Then we can have negative values of n2.
Negative values of, you see that if there is a negative value of n2, yes, it means there is a numerator in the s, there is a pole in the s. So, what I want is this, that this particular transfer function which you have written after all possible pole 0 cancellations have taken place. I am not retaining any pole over here. So, it means this final form, this n number has come after all cancellations have taken place. Again, by pole 0 cancellation I mean, as far as the mathematical model is concerned, it is the perfect pole 0 cancellation. The statement about robustness which I made, that the pole 0 cancellation which you show up in your mathematical model is not exact when you go to the actual system, but yes, it approximates to that value in the actual system as well, if the parameters do not wander too much around the nominal values. So his point may please be noted. When I am defining the type number, I am really not taking that, assuming that there will be an s in the numerator. I am assuming that this particular transfer function which you have written has been written after all possible pole 0, exact pole 0 cancellations if any in the model. Okay? I hope this point is also well taken. Fine then. If that is okay, then let us take one by one the situations. Keep GS in mind. GS is equal to K sigma I S minus pi I S minus Zi S to the power of n J S minus Pj. This is the transfer function. Now help me please. Consider a type 0 system. First of all, can you give me a physical example of a type 0 system? We have really put in lot of effort on modeling, lot of time was spent on modeling. So in between some questions if I give you, you must answer it. Type 0 system, I want some physical examples. Proportional control?
A constant amplifier.
No. Okay, a constant amplifier. You see, you give, this is a device you have given which can be modeled as a type constant amplifier where it's a 0 order system rather. You see, a type 0 system will have dynamics as well. You give me a complete control system. You get, his answer is right, I don't challenge that. But an amplifier is not a control system by itself. I want you to give me an example of a feedback control system with dynamics but type 0 system.
Sir, any second order system with a general equation?
That I could answer. That is very visible here. I want physical example. The mathematically it is visible here. You see, why second order? You simply take S here in
Motor, sir.
A motor.
Hydraulic temperature control.
temperature control system. Yes. You recall the models. A temperature control system, the model was obtained as some K over S plus 1. That was the model. Liquid level control system, the model was obtained as K over S plus 1. There could be, I think in one model it was a second order term, S plus 1 into S plus 2, but still it's a type 0 system. Now the general statement motor control is wrong because the motor transfer function was K over S into S plus 1. It's a type 1 system, S into S plus 1. But I don't say that your answer motor control is totally wrong. But if you use your motor in speed control application, then it is a type 0 system because your transfer function with respect to speed was K over S plus 1. Please see that. You have to equip yourself with all these things. When I am asking a question, I am asking with respect to physical interpretation. Take a motor control system but use motor in speed application, it's a type 0 system. But if you use your motor in a position control application, it's a type 1 system. You see, order, somebody said that take any second order system. In defining the type of a system, order of the system is not important. It could be an nth order system, it could be 100th order system. What is important is the number of integrators in the forward path. The order is not important. You could take any order. How many integrators are there in the forward path? That is why I wanted you to recall the type of models we have derived. Okay, you go back and look at your notes and you will find that these statements are right. The temperature control examples, liquid level control examples we have discussed in the class. We have modeled them as type 0 system. Speed control as type 0 while position control as type 1. Any example of type 2 please, since we are discussing it. We have discussed some example either in the class or in the tutorial, that I don't remember at present. But any example of type 2 system you could give me. At least one example comes to my head which I have discussed, maybe in the tutorial.
Satellite control.
Yes. Attitude control of a satellite was an example whose model we obtained as K over S squared. Okay, simplified model, and S squared means, well, it's a second order system, but this second order system has got two integrators in the forward path and hence it's a type 2 system. So please see that I have not given you any example to my mind which is a type 3 system. I have not given you any example. It does not mean that system example cannot exist, but I simply say that mostly it does not exist. Okay. However, in a very specific design, you may really, because of very high demand on steady state, you see, I may give you an example. Some of the radar systems could be type 3 system. Could you tell me why? Very interesting discussion is going on, that is why you say I am making this statement. Some of these radar systems, antenna control systems could be type 3 systems even. When I said that most of these systems will be either type 0, type 1, type 2 except in very specific situation. Can you imagine that an antenna control system will be a type 3 system? Why? If it is yes, then the reason should be given. Speed से तो कुछ इसका आंसर नहीं. You see that it depends, you should answer it this way. If a type 3 system comes, it means it is very much dependent upon the nature of the input. You take a numerical control, a machine tool is not going to revolve and give you a job like this, it will be a ramp, a parabolic shape or some systematic shape. But in a case of antenna control system, what is the input? The input is maneuvering of the target aircraft. You see that you are after all targeting your antenna on the aircraft where your missile is to land. If there is no static accuracy with respect to the enemy's aircraft, in that particular case the missile cannot land at the appropriate place. So you want, if you find that it is the military aircraft you are pointing, so military aircraft means the maneuvering will be so fast that you want the capability on static accuracy to a very high standards. So in that particular case you may require that the acceleration error should also be 0. As you will see that with a type 2 system, error to acceleration inputs cannot be 0. The input acceleration input should also give you a 0 error, that may be a demand on the system. In that particular case you may design a type 3 system in that particular case, but please note that stability of the type 3 system is a very risky proposition. So it means you will have to make a very careful design so that you can really, you have not to pay a heavy price in terms of instability of the system. So the example I am giving you, that type 3 system possibility is also not ruled out, but such applications are rare and mostly we go for type 0, type 1 and type 2 systems. This point of type 3 system will become further clear when I give the acceleration error constants. I will comment on this again. Type 0 system, since you have referred to this point, help me please, what is the value of Kp for a type 0 system? This is equal to, look at this point, it is k pi I s minus zi over s minus pj, s is equal to 0. So what is the steady state error to step inputs? The steady state error to step inputs is 1 over 1 plus kp, which is finite. Okay. How about the steady state error to ramp input, that is what is kV? I think let me not write it, you can keep on answering quickly. What is kV in this case please? A type 0 system, I want you to give me the value of kV. I am sorry, take it DSGS total including the controller. Is kV 0? Is it the answer given by him is correct? kV is 0. So what is steady state error to ramp input? Infinity. Same will be the situation with Ka please. Ka is 0 and the steady state error to acceleration inputs is infinity. So it means, please see that your type 0 system cannot meet high demands on steady state accuracy. It can at the most give you reasonable steady state behavior if the inputs are only the step inputs or the constant inputs. This should be very clear now. A type 0 system cannot meet high accuracy demands. So if high accuracy demand is there, as you will see, you will have to intentionally introduce integrators in the forward path. Okay. Is the table complete please? Kv is equal to 0 and Ka is equal to 0 and hence steady state errors is equal to infinity. Anyone who could not get this point please? I hope this is okay with all of you. In that case I go to type 1 system please. I think you can immediately do the necessary calculations. I will be interested more in the conclusions based on this. S only, J S minus Pj. Look at this type 1 system please. A type 1 system will always have Kp equal to infinity and therefore ESS is equal to 0 as far as step inputs are concerned. And therefore, whenever a type 1 system is involved, you should not calculate the steady state error, you see. In one of the tutorial classes, one of you observed that the steady state error is always 0. Okay? It means it has got reasonably good steady state accuracy, steady state behavior. But if you see kV, kV in this particular case is limit s tends to 0 s ds gs, and you can say that this is equal to k pi I s minus z I over pi j s minus p j, s is equal to 0, a finite value. So, it means a type 1 system will give you a finite value of kV and hence steady state error for ramp inputs. Okay? But now I leave it to you, you calculate Ka. Ka in this particular case will turn out to be 0 and hence the steady state error to acceleration inputs is infinity. So, it means by introducing one integrator in the forward path, you have improved the steady state behavior of the system. You have improved this. Now, lastly, the type 2 system. Type 2 system, if I take, well, ds gs is equal to k pi I s minus z I over s squared pi j s minus p j. Well, the calculations will immediately come. Kp is equal to infinity, Kv is equal to infinity, and Ka is a finite value. So, it means a type 2 system will have 0 steady state errors to both step and ramp inputs. A good system from the point of view of steady state accuracy, but you please note that the price is being heavily paid, and the price is in terms of stability requirements. Two integrators in the forward path are going to create problems for you as far as stability design is concerned. Okay? So, the situation is not that rosy. That is why we have to strike a compromise, a trade off between the accuracy and stability. But this I see, a type 2 system will have 0 steady state error to both step and ramp, and a finite steady state error to acceleration inputs. Now, you fit in the argument I gave for the antenna position control system. If you want the error to be 0 for acceleration types of inputs also, in that particular case you will like to go for one more integrator, and hence it will become a type 3 system. And such applications are rare, very few, wherein you require 3 integrators in the forward path. In typical industrial control applications, I will say you are mostly satisfied. General statements I am making, very general application where the user has not given a very specific demand to you. In that case, I say that you are mostly satisfied with 0 steady state error to step inputs and finite steady state error to ramp inputs. If the user has not specified anything else, in that case mostly what you do is, in that particular case, can I make a statement that if the system has an integrator inbuilt into it, you may like to go for a position or a PD controller. But if the system has not an integrator inbuilt into it, you may like to settle for a PI controller. Is it okay? Is this statement okay, please? I am making a statement that in general, most of the control systems we come across, general applications where there is no specific demand from the user, in that particular case a 0 steady state error to step and a finite steady state error to ramp is more or less okay. So, as a general guideline, if you have to make a quick decision as to what type of controller you want, in that particular case you look at the plant. If the plant is a type 0 system, in that particular case, well, if you go for an integrator in the loop, that will be better, unless the user has given you a specific demand, because the steady state accuracy will be improved. But if the plant itself has got an integrator, for example, the motor example you gave in the position control application, in that particular case you may try, at least try whether the performance is satisfactory for only position control or with a PD controller, because a PD controller will not increase the type number of the system, while an integrator increases the type number of the system. Is it okay, please?
So can a Only a D control decrease the type number of a system.
Only a D control, yes, a question please. A D control only if you take in the forward path. Again, it is a question where the cancellation comes. So if it is a type 0 system, it does not, otherwise it will, mathematically speaking, yes. But since the D control, the derivative control does not affect the steady state error of the system, normally only D control is never used in practice. It is a PD control, proportional, proportional derivative, proportional integral, proportional integral derivative. These are the combinations we use. Mathematically, yes, on the basis of whatever cancellations you get, your answer will come on that, because you are working on a model. Okay. So, by cancellations, whatever answer you get, it is a valid answer, but practically only D control is not used because it does not affect the steady state behavior, and you go for PD type of control in practice where the type number will not be affected. Okay. Any other question please? If this is okay, then look at the time and the requirement of a design example. So, let me make an attempt, otherwise I will probably leave it in between and complete it in the tutorial, because next time definitely I want to go for a new topic. I take a complete design example as a position control example you have just now referred to. This is your theta r. This, let me say, is a DS, a controller. This I take as the plant. I have a typical value in mind. I will not give you the numerical values here. S plus 361.2, it comes from some specific values. So, I am using those values over here, theta L the load, and I want to design a controller DS for this particular system. Keep the physical system in mind. The physical system is a position control system. It is an amplifier, it has a motor, it is a power amplifier, it has a gear train, it has everything which a position control system has. So, I am modeling it this way so that I can go ahead. Suitable numerical values of all the parameters have given me this value of GS. And naturally, in this particular case, I will first like to try only a position controller, because the system is a type 1 system. Okay. So, in that case, I try only an amplifier Ka and see whether my performance requirements are satisfied or not. So, with this Ka, I find DSGS is equal to 4500 Ka divided by S into S plus 361.2. If my performance requirements are not satisfied with only Ka, then I may go for a PD controller or a Pi controller or even a PID controller. So, in this particular case, you find the characteristic equation, I want to determine the zeta and omega, and fortunately please note the characteristic equation for this system is coming out to be in the standard second order form. Okay. You can just see S squared plus 361.2 S plus 4500 Ka equal to 0 is the characteristic equation, and this is a function of Ka only. Now, look at these terms. These you are very well equipped to make the calculations. From the characteristic equation given to you, I get these values of different parameters. You can just take down these values and satisfy yourself that these values are correct just by applying the basic relations we have discussed so many times. The natural frequency omega n is 4500 Ka under the root, a function of Ka. The damping is a function of Ka. These are the closed loop poles of the system, again a function of Ka. Steady state error in this particular case turns out to be this. Tell me please whether this steady state error is an error to step input or to ramp input. I have not written here. Should it be to step input or to ramp input please? No. For step input it is decidedly 0. How can I give it in this expression? I have not written for you, you have to note it that this has to be ramp input, neither the step nor the acceleration, because I know that it is a type 1 system. For step input it is 0 and for acceleration input it is infinity. So, it has to be finite only for ramp input, and therefore, for ramp input the steady state error turns out to be this value. Okay. So, these are the basic relationships I have. So, now let me take some numerical values please. I hope you have noted down. Okay, all of you just verify. If there is any error, you do please inform me about that. Otherwise, hopefully the calculations are right. Now let me take the value of Ka equal to 7.247. Why did I take this value? Just for the sake of comparison, I have taken a value which gives me zeta equal to 1. So you see that I have used this expression only to get the value of Ka I am giving you. Okay, don't worry about the numerical calculations at this stage. Look at the concept. I have taken a value of Ka so that zeta equal to 1, a critically damped case. Okay, corresponding to this zeta, don't worry about these statements, corresponding to this zeta equal to 1, look at the response I am going to get. The response for the standard second order system, I am going to get this. Now I know that for a general application, this value of Ka is equal to 7.247 may not be acceptable to you. The reason being that the settling time for zeta is equal to 1 is reasonably high. Unless the user tells you that I want zeta is equal to 1, you will not like to design for a zeta equal to 1 because the settling time is reasonably high. Of course, rise time will also be, rise time as such is not defined because what is rise time in this case, please? Just you apply. Literally, if you apply your definition, it is infinity. Rise time, because it will cut that axis only at infinity. So rise time actually is defined for underdamped system. Let me not use the word rise time for this application, but settling time I can of course define, and the settling time in this particular case is reasonably large, as we have discussed from the settling time or normalized settling time versus zeta curve, you can recall. So in this particular case, it means I will really like to go for a moderate value of zeta, and now using the same formula I get Ka is equal to 14.5, which gives me zeta is equal to 0.707, which gives me peak overshoot is equal to 4.3%. All the calculations you can verify easily. Now you can see that as far as peak overshoot is concerned, maybe it is acceptable. 4.3% is not a large peak overshoot. Well, zeta is equal to 0.707 is a good value because the settling time in this particular case is going to be low, probably the lowest settling time, probably the lowest, you see, and correspondingly the rise time in this particular case will be low, the peak time will be low, everything is quite good, and 4.3 is the only price I am paying. What is the price I am paying? Overshoot of 4.3, which looks quite reasonable. Okay. So it means in this particular case, this value is all right. Now you see that what is the corresponding steady state error? Let me go back to the original slide. The steady state error in this particular case is 0.0803 divided by Ka. The value of Ka you have taken as 14.5. So this is the steady state error. So I can simply say that in this particular case, the steady state error is fixed at this particular value 0.0803 divided by Ka, where Ka is equal to 14.5. But if you want to improve on the steady state error, what you will do? You will have to increase the value of Ka. So it means if the steady state accuracy demand is high, you will have to take the large values of Ka. In that particular case, you will have to allow lower values of zeta, though zeta is equal to 0.7 is moderate. So if you allow lower values of zeta, what will happen? The price being paid is that the peak overshoot will increase. So it means the situation of no further trade-off will come, that you will say that no more values of Ka if the peak overshoot is exceeding the limit you have imposed on the system. After all, otherwise the system may become unstable. Let me say that the limit you have imposed on the system is that, look, you see, your peak overshoot should not be higher than 25%. Now you see, though the settling time will be larger, but still you are allowing the lower values of zeta because you want to get better steady state accuracy. You want to get better steady state accuracy, please. So in that particular case, you have allowed 25% over here, and this corresponds to zeta is equal to 0.5. And this zeta is equal to 0.5 is 45.3 in this particular case, and the steady state error correspondingly is 0.0803 divided by Ka. Now you will say to the user, to the person for whom you are designing the system, hands off, because you will not like to decrease the steady state error further. The reason being that this will be dangerously close to instability. So, as far as proportional control is concerned, you have reached the limits. Now, since I cannot take PD and PI controller, so in just 1 minute you give me the clue. So, if you want to improve the steady state accuracy further, what will you do, please? Still you do not want this particular 25% requirement to be violated. One thing is there that yes, first thing is that PD control is also possible. You can try this, please. Though PD control as such does not, the derivative control as such directly does not affect the steady state error, but what it will do, you see that the derivative action will provide for the damping. So, what you do is it is going to allow you to take larger values of Ka without violating the requirements of 25% of overshoot. A simple exercise for you. You replace your Ka by Kc plus Kd by S and satisfy yourself that it will allow you to increase the value of Kc, the proportional term, because the damping is being provided, additional damping is being provided by the derivative term. So, a PD controller can also improve the steady state error, please see. The reason being that, well, the increase in Ka, the risk was the damping was being reduced. Well, now you are adding a derivative term, and additional friction into the system is being put in, so that the damping is restrained at the required value, and hence it is going to permit a higher value of Ka. A higher value of Ka means a lower steady state error. And second, of course, you have answered, PI control is definitely going to reduce the steady state error to 0. The only thing is this, that you have to be cautious in the design that your transient accuracy requirements are also satisfied. And these things cannot come analytically. Graphical methods, the root locus method and the frequency domain methods, very well established methods of control system design, will help you design the values of PD, PI or PID controllers, so that the steady state and transient accuracy requirements are satisfied. And this is the subject of discussion next time. The root locus method we will start with. Thank you.